Greetings, our solar system extends from the Sun to about 15 million kilometers, around 1.58 light-years. This is where the Oort cloud ends, a region containing a large number of icy objects from the formation of the solar system, as well as long-period comets. The majority of its mass is concentrated in an area of only 4.5 billion kilometers, which is where the Sun and its orbiting planets are located. When we wonder what's above and below Earth, it's simple because we are subject to gravity. However, in space, there is no up or down. We have to navigate based on the orbital inclination of planets and their orbits around the Sun. Planets orbit the Sun in the same plane. Earth revolves around the Sun in a plane called the ecliptic, and the orbits of other planets are close to it. In contrast, dwarf planets like Pluto and other objects have very different orbits. The 8 major planets are in the same plane but have different speeds around the Sun. That's why we sometimes observe transits and conjunctions from Earth. When we look at the night sky, we usually find the planets in the same plane. The inclination occurs because Earth's equatorial plane is tilted 23.4 degrees relative to its orbit around the Sun. In space, we can imaginarily consider, starting from the ecliptic, that this is above and this is below the solar system. If we start from the counterclockwise rotation of the planets, below the plane of the 8 planets and also above it, we can find the orbits of Pluto, Haumea, Makemake, and a large number of minor objects, icy asteroids, and comets, some with highly inclined and retrograde orbits compared to the planets. Oumuamua is the interstellar object shaped like a flying cigar that came from above at an average speed of 26.3 kilometers per second and passed below the ecliptic before rising again, accelerated by the Sun's gravity. Borisov was another interstellar object that came from below the ecliptic and exited above. The speed of this object was higher, at least 32.8 kilometers per second. We wonder if there is something above or below the solar system that is sending these objects into the region of the planets. Beyond Neptune, there's the Kuiper belt, filled with minor objects that orbit a few degrees above or below the ecliptic, and some with highly inclined orbits, like Pluto. As we move away from the Sun, massive bodies are left behind, and there's more variety of minor objects, either alone or grouped in clouds or rings. The space around the Sun becomes increasingly empty. After the discovery of Pluto, theoretical speculation arose about more regions from which comets would come, similar to the asteroid belt. It wasn't until 1992 that the first object of the Kuiper belt, the minor planet Albion, was discovered. Since then, we've discovered many more objects in this zone, validating the theory. It extends from the orbit of Neptune to 30 astronomical units and up to 50 astronomical units from the Sun, where Pluto, Haumea, Makemake, and other irregular minor bodies are located. Beyond that, it's estimated that there's a massive body of at least 5 Earth masses disrupting the orbits of some Kuiper belt objects, known as Planet 9, and it would be located between 400 and 800 astronomical units from the Sun. The Voyager, which is 152 astronomical units away, has a long way to go before reaching this region. Initially, the Kuiper belt was thought to be the origin of comets, but the true source of long-period comets is about 1,000 times farther. It's a toroidal-shaped cloud enveloping our solar system that could span from 2,000 to over 100,000 astronomical units. This is known as the Oort cloud, though its existence is purely speculative due to its vast distance. It could host 100 trillion bodies with diameters exceeding 1 kilometer. This cloud developed closer to the Sun around 4.6 billion years ago. Subsequently, the gas giants altered their orbits, scattering objects much farther away, some of which caused violent collisions giving rise to the planets, while the Oort cloud continued accumulating material from nearby stars. Most objects in this cloud didn't form near the Sun. In theory, they might be protoplanetary disks from other stars. Nearby stars and galactic tides gradually shaped this cloud and the orbits of its comets, making them more circular. This theory supports the Oort cloud being approximately spherical. Just as the Moon affects ocean tides, the tidal forces of the Milky Way also distort the orbits of objects in the Oort cloud. Beyond a light-year from the Sun's gravity weakens, and the galactic forces exert their influence. Starting around 1.58 light-years, beyond the Oort cloud, marks the theoretical edge of the solar system. Here, the Sun's influence wanes, and galactic tidal effects become more pronounced. Other nearby star systems and the galactic tides will affect the Oort cloud. Other star systems closer to the galactic core will experience even greater influence on their Oort clouds or asteroid belts. This is why we're in a privileged zone for life development, a relatively calm area. If we stick to the ecliptic plane of the planets, we know with certainty what we might encounter above and below, in quotes, the ecliptic of the 8 planets. Below the ecliptic, we'd encounter the Alpha Centauri system, the closest star system to ours, at an average of 4.3 light-years, visible mainly in the southern hemisphere. Above the ecliptic, we find Barnard's star at 5.9 light-years, a red dwarf, and Lumen 16, a binary brown dwarf, just beneath it. Wolf 359, a red dwarf at 7.8 light-years, would be slightly farther. Each of these stars would orbit the galactic core at different speeds. About every million years, around 12 stars approach the Sun within about 3 light-years on average. As we move away from our local Orion arm, it's evident that the solar system's ecliptic is inclined about 60.2 degrees to the galactic plane. However, the Milky Way's overall gravitational forces, not just the Sun's, guide its trajectory. Its speed of 220 kilometers per second keeps it safely distant from the galactic core, avoiding energy-intensive phenomena like supernovas. Around 25,000 light-years from the galactic center, the Sun orbits the galactic core, much like the solar system orbits the Sun. The Sun has completed about 20 orbits since its formation, making it about 20 galactic years old and expected to reach about 40 before its life cycle ends. Simultaneously, the Sun rotates on its axis about every 27 days, assuming we reference the equatorial region. This indicates a lack of tidal locking with the galaxy. Up and down in space is highly relative. Over large scales, the positions of objects can change over thousands to millions of years. Due to our short lifespans, we perceive the galactic panorama from a limited viewpoint. We imagine what's up and down based on planetary movements. Earth isn't perfectly aligned with the galactic plane. The Sun and the galaxy tug at each other, causing oscillations above and below the galactic plane. As the Sun orbits the galaxy, the solar system behaves like a satellite, and the galactic core acts as a planet. Numerous stars join the Sun, making up the Orion arm, distributed across a vast expanse of thousands of light-years. Most of these stars lie in the galactic plane, though some deviate from it, similar to our solar system. In navigation through space, using coordinates relative to a reference point, usually the destination, is essential. The vastness of space demands reliance on destination or reference objects, considering both velocity and direction. Space distances are immense, rendering our Earth-based calculations insignificant when traversing space. The profound sense of losing Earth would be akin to ancient mariners losing sight of the coast. In the realm of space, we face enormous, hostile forces, subject to multiple gravitational influences and galactic tides. If you enjoyed this video, please like and subscribe, share on social media, and leave your comments.